Okay, this is section 2.1. We're going to start an introduction to logic. Yep, this is what we're going to do. Okay, I'm going to write a statement and then the negation of it. So my statement is, my dog Strummer is a good boy. So that's the statement P, and P is true. So the negation of that, where we have this is a tilde. You may hear people say this as not P, meaning the negation, not true. Strummer is not a good boy. I hope you didn't hear me say that. Yeah, just did that. Okay. In logic, we use these quantifiers. We use it in math a lot. You may see it in other math courses. So like these universal ones, all, none. Think of that differently than other quantifiers such as some. So existential quantifiers. I think I was saying qualifiers, but they're quantifiers. My bad. So let's negate both of these. Well, the negation of all students like hamburgers is we just need at least one. So some students do not like hamburgers. And look at this. Some people like mathematics. Well, the negation of some would be no people like mathematics. Or you could say all people do not like mathematics. Okay, truth tables. We'll spend more time on this. So here are the two possible cases for P. P is either true or false, and then the negation. So here's the conjunction, the and. This is the symbol for and. So here this is P and Q. So let's kind of just look at this for a second. So when we have and, if we have two statements, they both must be true to make the conjunction true. Consider 2 plus 2 equals 4 and 3 plus 1 equals 5. Well, in this case, P is true, but the Q, the second part, is false. Therefore, when we put them together, it's false. For it to be true, we would have to simply change this, and 3 plus 1 equals 4. Now they're both true, therefore the conjunction is true. Let's compare that to the disjunction, an or. So P or Q. Well, with an or, we just need one of the things to be true. So notice in the truth table, now we have 3 truths because we have at least one of them or both being true. The only time it's false is when they're both false. So if I had 2 plus 2 equals 4 or 3 plus 1 equals 5, okay, this is true because the first statement is true. And once we have one true statement with a disjunction, the P or Q, since P is true, the disjunction is true. Oh, I just jumped into it right away. So here's a conjecture. Notice this is inside the parentheses. So I'm saying not P and Q is equal to not P and not Q. The reason we may think this is true, hence the conjecture, is it looks like the distributive property should work. That the tilde, the not symbol, should just distribute to each of those terms. Well, let's see if it works. Now, when you start one of these truth tables, they always start like this. True, true, false, false. Then make Q true, false, true, false. If you don't start that way, I cannot follow your work. And this is the normal way to start anyway. This is the convention. So we start this way. Now notice how I set up this table. I want inside the parentheses first, which is P and Q. I have that right next to my PQ. So there's true, false, false, false. Now I'm going to negate this column. So I'm just focusing here. And the negation is false, true, true, true. Okay, now I'm going to do the not P column, the negation of P. Well, that would be false, false, true, true. Then I'm going to negate Q, which is here. That would be false, true, false, true. And I see there's a typo here. This should be an and. My bad. The publisher, I'll blame it on them. So, not P and not Q. False, false, false. False, true, false. True, false, false. Only with the true, true. So here's what we just did. Let me change color. This side, the left-hand side of the equal sign, is this. That's this column. The right-hand side is this column. Notice that the entries are not the same. Therefore, this is false. This is not true. The not operator does not distribute across the conjunction and. Okay, if-then statements. They're rather important, especially in math. So if P, then Q. So we do the arrow there for the if. This is a rather tricky table to convince yourself that this is true. That if P is true, then and Q is true, then if P then Q is true. It gets tricky from there. So let's look at this. Okay, here's my P. This is my hypothesis. If you earn 70%, then my conclusion is Q, then you will pass Math 4A. I think of this as, did I keep the promise? Okay. So if you earn 70% and then you passed, yes, I kept the promise. It's true. Now here, if you earn 70%, which is true, and then I do not pass you, Q is false, then I broke the promise right here. So the conditional is false. Now, let's look at these last two. If you did not earn 70% and you passed 4A, well, that's true because we don't really have enough information here with the hypothesis P, because maybe you earned 90% and you passed. Maybe you earned 69.8% and you passed, but at least the promise was kept. And here, think of the promise. If you did not earn 70% and you did not pass 4A, then I kept the promise and the implication is true. You're gonna have to think about that, I think. Okay. Here we go. We need to know these three related implication statements. So if P, then Q. So that's P arrow to Q. P implies Q. I think of it this way as well. If Q, then P, or Q implies P, that's called the converse. It's kind of reading it backwards. If I negate the hypothesis and then negate the conclusion, it's not P implies not Q. And then the contrapositive is if not Q, then not P. And I'm going to look at these with an example, and we'll see which of these implication statements is always true. So let's write these. So my statement, if I'm in San Francisco, then I am in California. That's true. The converse is if I am in California, then I am in San Francisco. Is that always true? No, because I'm in Bakersfield. So the converse, not always true. Sometimes it is. Look at the inverse. If I am not in San Francisco, then I am not in California. Well, that's not always true because I'm in Bakersfield, so I am not in San Francisco, but I'm still in California. So again, not always true. Now, the contrapositive. If I am not in California, then I am not in San Francisco. That's always true. It's logically equivalent to the statement. You may want to practice this. Make up your own conditional and write these and then check to see, to convince yourself that the contrapositive is always true. Now I'm going to finish with these things which you may have learned are syllogisms. Philosophers don't really use this kind of logic anymore, but it is valid reasoning. So if you've got a true hypothesis, all cats like fish. So we're assuming this is true. Then the conclusion has to follow from that hypothesis. If Felix is a cat, then Felix likes fish. So this is valid reasoning. And the only way to attack reasoning like this is you have to argue the hypothesis. Because maybe someone has a cat that does not like fish. That would be a counterexample, and then the hypothesis fails, therefore the reasoning would fail. That's it.